We're continuing with section 17.2, Stokes theorem. And one way of using Stokes theorem is when we don't like one side of the, we don't like to compute one side of the Stokes theorem, and we use the other side to compute the side that we don't like. Or it's more computational. Here, example, to compute the surface integral of curl of f over the S, and where f of x and y and z is xc, yz, xy, and s is the part of the sphere, x squared plus y squared plus z squared equal to 25 inside the cylinder, x squared plus y squared equal to 16 above the xy plane. So I know this is the right side of this one is the right side of the Stokes theorem. And the left side, what is the left side? The left side is the contour integral over the boundary of S of f dr. If I want to compute the right side, I have to find the curl and then parameterize it in the spherical coordinates and parameterize the path, parameterize the surface that way also, and then compute lots of sine and cosine. So I'll try my other side, which seems like less work for me. And so and that was not a good pawn, but it was. And so the integral of f dr over the boundary, I have to parameterize the boundary first. R of t, x squared plus y squared equal to 16. Let me show you the picture. It's the sphere, but then piece of the sphere that is inside the cylinder. So basically, x and y is still going to follow the cylinder, which is 4 cosine t and 4 sine of t. And if we keep it that way, and your orientation is this way, that would be the right hand rule. And what about z? Z can be computed by basically over the intersection of the two. Z is going to be, z squared is going to be equal to 9. So because we have the upper part, this is going to just be 3. And then r prime of t is going to be negative 4 sine of t, 4 cosine of t, and 0. Now, use the parameterization to parameterize f. So f of r of t is equal to x times z, which is 12 cosine of t, y times z, which is 12 sine of t, and then x times y, which is 16 times sine of t cosine of t. And I'm going to call this one 8. So I'm going to replace that one with 8 sine of 2t for now. So it won't be too messy in here. And so now compute f dot dr, and the parameterization was t between 0 and 2 pi. F dot dr gives me negative 4 sine of t times 12 cosine of t is negative 40 8 sine of t cosine of t, then 12 sine of t 4 cosine of t plus 48 sine of t cosine of t, and the last coordinate is just 0, and integral from 0 to 2 pi, 0 to 2 pi dt. And if you compute this, you're just going to get 0 inside, and therefore 0 in integral. So this was a bit easier than computing the surface integral that was original. And so we use that to compute the surface integral, and that is 0. Now, next, let's do one eye-clicker question. Let S, eye-clicker question 17.2b, let S be an orientable surface in R3, let C be the boundary of S, and let f of x and y and z be x and y and z, g of x and y and z be y and z and x. What does Stokes' theorem tell you about the following values? So P equal to the contour integral over C of f dr, and Q equal to contour integral of G dr, and contour line integral G dr. And so the first line integral should be equal to, according to the Stokes' theorem, should be equal to the surface integral of curl of f dx. And the second one should be equal to the surface integral curl of g dx. And so now first let's compute curl of f and curl of g to see if that gives us any information. Curl of f is equal to I, j, k, partial respect to x, partial respect to y, partial respect to z, x, y, z. And so when you compute this, you realize that it's 0 times I, then it's 0 times j, and it's 0 times k, so it's 0 vector. Now, curl of g is equal to I, j, k, and partial respect to x, partial respect to y, partial respect to z, y, z, x. And if you compute this one, it's going to be 1 times negative 1 times I, and then it would be 1 times negative 1 times j, and it would be a negative k. Okay, so this one's non-zero. The first one is 0. First one being 0 makes this this surface integral equal to 0. The second one, so the second one not being 0, the second one not being 0 doesn't give me as much information, because what if the basically after the dot product I get a 0 vector, or after dot product I get a non-zero value, not 0 vector, but get a 0 value or non-zero value. So it doesn't tell me as much as the first part tells me. And so this is B, P equal to 0, but Q might be 0 or non-zero. So, and some sort of a fun comics to look at this point, curl and circulations in Green and Stokes' theorem. Green's and Stokes' theorem both say that if a vector field pushes stuff counterclockwise around around the boundary of a surface of a surface in R2, then it rotates